All right, hi everybody. Today we're going to be looking at 14.4, which is the tangent problem and the derivative. So we're going to start out first by looking at this first graph that you would do back in algebra, like the good old days of middle school, and y equals 2x minus 1. So if I was going to graph this, write them down at -1, we got a slope of 2. And I have this nice linear function. All right, if I pick any 2 points on this line, if I pick between here and here, the slope is 2. If I pick between here and here, the slope is 2. If I pick some arbitrary point here, between this arbitrary point here, the slope is 2. So the slope is always the same anywhere along the curve. Well, the difference is now in calculus, we're not going to be looking at linear functions. We're going to be looking at graphs that look like this. And so if I pick any 2 points on this curve, like let's say I pick a point here and here, the slope between those 2 points is going to be very different if I pick between here and here. Or if I picked a point between here and here. So because it's a curve, the slope changes everywhere along the curve. So to combat that, what happens is we pick an arbitrary point, and we have a tangent line at that point. So if I draw a tangent line at that point, if I can find the slope of the tangent line, then that is also going to be the slope on the curve at that point. So if I redraw that curve, okay, so if I look here and I draw a tangent line at A, I would say that the slope at this tangent line, if I drew this tangent line right there, that line is going to have a positive slope. So I'm going to write that over on the side. A positive slope. If I look at B, well, that's really going to be a tangent line that's a horizontal line. So my slope at B would be the slope of a horizontal line, which would be 0. If I look at C, I got a very steep tangent line, but either way, it's still going to be a negative slope. And then at D, if I drew a tangent line in, I'm going to have a positive slope. So anywhere along the curve could be different slopes. And so the derivative helps us find what that slope is at any specific point along the curve. Because again, if it's linear, we don't need the derivative so much because the slope is going to be the same everywhere along the curve. But in a function that is curved, that slope is very, very different depending on where you are on that curve. Okay, so some terminology here. In a linear function, our slope is that average rate of change. Okay, for a curved function, the derivative. Okay, so calculus is hard for a lot of reasons. One of those reasons is they could ask the same question 4 different ways and they could use different language for it. So if they ask for find the slope of the tangent line, that's really just saying, okay, really just find me the derivative. If it says find me the instantaneous rate of change, that's another way of just saying, find me the derivative. If you see the word differentiate, that means find the derivative. Okay? If you see instantaneous velocity, again, that's the same thing as find the derivative. Okay, so all of those mean the exact same thing. Now, in terms of notation, Okay, so if I say find the derivative, you might see this. It's a dy over dx. That means find the derivative. You might see f prime of x. That means find the derivative. You might see just y prime. That means find the derivative. So we have some notation and we have some words that all mean take the derivative. And remember, when you're taking a derivative, all you are finding is the slope of the tangent line or the slope at a specific point.